Symbols, match them to their description. So delta V, delta means that triangle is a delta. That means change, and that's change in velocity. So that's B. A is just acceleration. Let me cross them out as I go. Although maybe I'll use them twice. A is acceleration, which is letter E, which is kind of confusing. Sorry about that. Delta X is change in position or displacement. Got two names for that. And X is just position, F. Let's see, if I were to do these other ones, change in time, that would be delta T. And velocity is just V. And position, hey, position's on here twice, so that could be A. That's X. Which of the following are scalars? Scalars are quantities that don't have direction to them. Vectors, those are the ones that do have direction. So distance doesn't have direction. If I say I hiked a distance of 3 meters or 3 kilometers, you wouldn't know which way I went. But if I said I had a displacement, you would want to know which direction. My displacement was 3 kilometers to the right or the left. So that's not a scalar, that's a vector. Velocity has to include direction. So velocity would be 3 meters per second upward or downward. Speed is just how fast you're going. So if you're falling, if you throw something up in the air, as it goes up and comes down, it goes up right here with about the same speed as it comes down. But the velocity is different. The velocity is positive here and negative there. Acceleration, you can accelerate to the right or to the left, so that's a vector. So all three of these have direction. They're all vectors. These are the only two that don't. They're scalars. We have a student walking from some point to another point. Now this is going to be different on your exam. The exact scenario. You just have to be really comfortable with what these terms mean down here and how to deal with them. So in this particular case, somebody starts at A and walks to B and then goes back to C. So let's do that. And then we're given a time. What's delta T? Delta T is the time that went by. So it says when the student leaves A, the watch reads 8 o'clock, 15 minutes, 2 seconds. And when he reaches C, it's 8 o'clock, 15 minutes, 18 seconds. So 18 minus 2 is 16. This was a 16-second event. Displacement is change in position for the entire thing. So one way to do delta X is to do the final position minus the initial position. This is one way to do it. There's another way. So the final position right here is -2. And oh, sorry, that's the initial position. That's where he starts. So that's the initial position, and the final position is +2 meters. So if I want to find the displacement, it's going to be final position 2 meters minus -2 meters, which is 4 meters. So the answer here is 4 meters. Now what you can do is you could say, here's where he starts, and here's where he ends. Forget about the fact that he went over to here and then back. If he starts here and goes to there, he's displaced 1, 2, 3, 4 meters to the right. So it's +4 meters. That's the answer. Let me write it over there again, so it's a little bit easier to read. What overall distance did he travel? So for distance, we need to add up every meter that he traveled, whether it's positive or negative, we just add it. With displacement, really what we're doing is we're adding 1, 2, 3, 4, 5, 6, 7, 8, 9, that he goes to the right, and then we're subtracting 1, 2, 3, 4, 5 that he goes to the left. So we add positive displacement, we subtract negative displacement, we get 4. But with distance, we just say, okay, he went 9, and then he went 4. 9 plus 4 is 13. Did I do that right? No. 1, 2, 3, 4, 5. So 9 plus 5 is 14. Average speed. So speed and velocity are different. Speed is distance over time, and velocity is displacement over time. So for speed, it's just going to be 14 meters over 16 seconds, and that's kind of an ugly number, 7/8, which would be 0.875, I think. 14 divided by 16, 0.875. I know that because I convert from English units to metric units a lot. Meters per second. And the velocity is displacement over time. So the displacement was 4 over 16 seconds. And that's an easy one. 4 divided by 16 is 0.25 meters per second. And both of those are positive because there was no negative numbers in the equation. Graph matching. I won't ask you to match all these graphs on the exam, but you'll have to match some of them. So these are position graphs, these are velocity graphs, these are acceleration graphs. And you can do these a variety of different ways. I'll maybe show you the easy way first, or for some people, the simple way, and then I'll show you the foolproof way. So the simple way is if the position graph is curved, there's acceleration. If it's an upward curve, there's positive acceleration. If it's a downward curve, there's negative acceleration. If there's no curve, there's no acceleration. If it's going up, there's positive velocity. If it's going down, there's negative velocity. So here's what we can do with that. This one has positive acceleration. So I need a velocity graph that's going up. So there we go. And the velocity graph is going up, and the acceleration graph should just be in the positive range. Here, I've got one that's negative acceleration, so I just need to see the velocity graph going down, and the acceleration should be negative the whole time. And then here, there's no acceleration, but this is going up, so we've got positive velocity, and acceleration is 0. Here, this is straight, so there's no acceleration. It's going down, so the velocity is negative, and there's no acceleration. So that's one way to do it. The other way to do it is to think about slopes. The slope of this at any given time gives me the velocity graph, and the slope of the velocity graph gives me acceleration, because velocity is the change in position, and that's what slope is, and acceleration is the change in our velocity. And again, slope is just telling us how fast things are changing. So I've got a negative slope, and then I've got 0 slope, and then I've got positive slope. This is going downhill, level, uphill. So I'm looking for velocity. It starts out negative, goes to 0, goes to positive. That's this one. So A is like G. And then once I get to G, I look at this, and this slope, this is a positive slope the whole time. So I just need acceleration to be positive the whole time. So that's I. Now B has a positive slope the whole time. So that tells us that velocity, and this is the same positive slope the whole time. It's going to be the same positive number the whole time. So B is velocity graph E. And since the velocity isn't changing, there's no slope here. That means there's no acceleration the whole time. So that's J. Now this one, I've got a positive slope, and then I've got 0 slope, and then a negative slope. So velocity needs to be positive, then 0, then negative. And that would be this. Here it's positive, here it's 0, and now it's negative. So that's h. And if you look at the slope of h, it's always negative. It's always the same negative slope, so the acceleration is always going to be negative. Okay. And finally d, it's a negative slope. It's the same negative slope, never changing, so I'm looking for a velocity that's negative and never changing, and that's f. And now there's no slope, always no slope, so there's always no acceleration, so that's j. So there you go, two different ways to do that. The correct units, time is seconds. This is an easy one. This will just be scrambled up. Speed is meters per second. Let me jump to velocity. That's also meters per second. The only difference is that speed is never negative, velocity is negative sometimes. Accelerations, meters per second, or meters per second squared. And then displacement is meters. Now, this is a ball that goes straight up and straight down, but I've shown it going over so that all these lines don't run into all those lines. It'd be a mess if I made it go like this and back down and put everything here. So you just have to fill in all these values. Given that this starts at time 0, it starts at a height of 0, it finishes at a height of 0, and the entire flight lasts some number of seconds. This is going to be an even number. It may not be 8. So what you do is you take the time for the entire flight, divide it by 2, and you put it here, because everything is symmetric. It takes the same amount of time to go up as it does to go down, assuming that there's no air resistance, and that's what you'll be assuming here. The acceleration, once it's in free fall, which means no air resistance, the acceleration everywhere is negative 10 meters per second squared. Negative 10 meters per second squared, and it doesn't stop accelerating even when it's at the top. Now, the next thing to do is, I think, figure out that, this velocity. So it goes up and it comes down, and as it goes up, it gets slower and slower and slower and slower, and then it comes down, it gets faster and faster. So right at the top, its velocity is 0. And you have to now figure out how fast was it when it first started up. So there's a formula you could use. You could use the acceleration formula. In fact, let me do that. Acceleration equals change in velocity over change in time. You've had enough experience with this. You ought to be able to put it in the triangle and then solve for change in velocity. So the acceleration is negative, I'll just put acceleration there, v. Excuse me. Getting ahead of myself. So v is on top in this case. Delta v is. Delta v is a times delta t. So if I'm looking for delta v, I can just multiply a times delta t. So for this flight going up from 0 seconds to 4 seconds, delta t is 4 seconds. Let me just write that. A equals delta v. Delta v equals a times delta t. So delta v equals negative 10 meters per second squared times 4 seconds. So negative 40 meters per second. So that's telling me that the change in velocity from here to here is negative 40. So it's losing 40 to get down to 0, and that means it has to start out at 40. And we know this whole thing is symmetric, so if it goes up at 40 meters per second, it's going to come down at negative 40 meters per second. Now, I could have done the same thing over here. I could have said, I could have used this formula, delta v equals a times delta t. From here, 4 seconds to 8 seconds, that's a time of 4 seconds, and the change in velocity is also going to be negative 40. So if I start out at 0, and I have a change of minus 40, then that's going to take me to negative 40. Now, without this formula, we've never really used that formula in this situation before. Just think about it. Acceleration of negative 10 meters per second squared means for every second that goes by, we lose 10 meters per second. So you can start here and say, if I start at 0 and I fall for 4 seconds, I'm going to lose 10, I'm going to lose 20, I'm going to lose 30, I'm going to lose 40, so I'm down to negative 40. Or you could say to yourself, what do I need to start at to get down to 0 after 4 seconds? And you could count backward. Well, 1 second before getting to the top would be going 10, and 2 seconds before getting to the top would be going 20, and 3 seconds before getting to the top would be going 30, and at the beginning it would be going 40. Some conversions. So it won't be these. I'm going to pick some stuff from this menagerie of equal quantities and have you do some conversions. So I've got 5 inches and I want to get that to centimeters. So I'm going to write 5 inches and then I'm going to multiply that by a fraction, and the fraction needs to cancel out inches and it needs to leave me with centimeters. So centimeters needs to be on top and inches needs to be on the bottom. So I can just look up here and find the relationship between inches and centimeters. 1 inch is 2.54 centimeters. 2.54. So what I'm doing here is, since this is equal to that, this divided by this is 1. And you can multiply anything by 1 and get the same thing, but the clever thing here is that I'm going to get different units. So inches on top, inches on the bottom, they cancel out and I'm left with centimeters. So I just need to multiply 5 times 2.54. 12.7. One and my two are running together there. Ugh, what a mess. Now 6 meters equals how many feet? Same thing. 6 meters, I'm going to multiply that in such a way that my meters get canceled out. So meters needs to go on the bottom and I'm left with feet. So I need to find out how many feet a meter is, or how many meters a foot is. 1 foot is 0.305 meters. So I need to multiply 6 times 1 and then divide that by 0.305. So basically I'm just doing 6 divided by 0.305. Did I do that right? I think that's right, but let me do it again. Just seems unfamiliar. And let's just see if it makes sense. So that would be 19.7 feet. Yeah, so a meter is a long step, and like if you imagine walking on the along the classroom floor, a meter is about 3 feet, but it's more. It's a little bit more than that. So 6 times 3 is 18. 19.7 is a little more than that. Physics problems, which directions are positive? Positive, so we do everything on this coordinate system like this. X and Y coordinate system. This direction is positive, this is negative. This direction is positive, this is negative. So the ones that are positive are rightward and downward. I'm not going to do all these, but I thought it'd be good to give you all the possibilities. So you have to tell whether, tell whether velocity, acceleration are positive, negative, or 0. All right, so let me just start out with these. This is a little backward from the way I usually do this. I might give you these two things and you have to match it to those. But here I'm giving you these and you have to generate these. No speed, but beginning to move rightward. So if you have no speed, then you have no velocity. Velocity is 0. And if you're starting to move to the right, then you're gaining. You're going to have positive velocity. So you're adding positive velocity. So your acceleration is positive. no speed but beginning to move to the left, so your velocity would be 0, but you would be starting to gain some velocity to the left, so you have negative acceleration. So this is like a car that's at the starting line, and it's just started to go this way. And then the second one, this is like a car that's at the starting line that's just starting to go that way. So it doesn't really have any speed yet, but it is accelerating. And this one doesn't have any speed yet, and it is accelerating. This is positive acceleration, this is negative. Moving leftward, speeding up. So now, imagine I've got a car that's going to the left. If it's going to the left, then the velocity is negative. And if it's going to the left and getting faster, then it's got negative acceleration. So anytime you see movement and speeding up, that means it's accelerating the same way it's going. Anytime you see movement and slowing down, that means the acceleration is in the opposite direction. So if you think of this as in terms of forces, F equals ma, forces cause accelerations. This car is moving to the left and it's getting faster. There's a force pushing it to the left. So the force and the movement are in the same direction. Now if it's moving to the leftward like this, but it's getting slower, then something's pushing it back to the right. It's accelerating to the right. So this would be negative velocity, but positive acceleration. Moving rightward, speeding up. So it's anytime something's speeding up, the velocity and the acceleration are in the same direction. Moving rightward and slowing down, well, the velocity is positive because it's moving rightward. If it's slowing down, the acceleration is opposite. So just going back over these. If there's no speed, then the velocity is 0. And if there's no speed and something is beginning to move rightward, acceleration is to the right. If it's beginning to move leftward, the acceleration is to the left. Now we go into moving things. If something's moving to the left and getting faster, then, well, the leftward means it's got negative acceleration. The fact that it's speeding up, negative velocity. The fact that it's speeding up means the acceleration is the same, also negative. Moving leftward, negative. Slowing down means the acceleration is opposite, so it's positive. Moving rightward, positive velocity. Speeding up means the acceleration is in the same direction. Moving rightward, positive velocity. Slowing down means the acceleration is in the opposite direction. I think we're about done with, I'm not quite. I was going to say we're about done with kinematics. So we've got to fill out this velocity versus time graph. Now, all you need for this section, really, is velocity equals displacement over time. And you just need to apply this formula to these different intervals. So first I'm going to do the 0 to 2 second interval, and then I'm going to do the 2 to 4 second interval, and then I'm going to do the 4 to 10 second interval, because I have a certain, the graph is doing one thing from 0 to 2, it's doing another thing from 2 to 4, it's doing another thing from 4 to 10. So the velocity from 0 to 2 equals the displacement, which is position goes from 0 to 8 meters, over delta t. Change in time is 0 to 2 seconds. So this is 4 meters per second. And that's the slope of that. That's a 4 meter per second slope. Slope of 4 is pretty steep. So I just darken this for the time from 0 to 2. Then from 2 to 4, the position goes from 8 to 8. Doesn't change. So really, we know what the answer is going to be. But let me finish. The time interval from 2 to 4 is 2 seconds. 0 meters divided by 2 seconds is 0 meters per second. So there's no velocity, 0 velocity from 2 to 4. Now the velocity from 4 seconds to 10 seconds is different. The displacement, look at the position here, look at the position there, it's going from 8 meters down to 0. So since I'm losing 8, the displacement is -8 meters. The time goes from 4 to 10. 10 minus 4 is 6 seconds. So 8 divided by 6 is going to be 1 1/3, but let me just do that. 8, let me make it negative here, divided by 6. 1.13, it's negative 1.13. Or sorry, negative 1.33. And that would be somewhere around here for the 4 second to 10 second interval. Almost done. Ball is dropped from a high place. The ball free falls for 9 seconds. So free falls, that tells us the acceleration is -10 meters per second squared, or about. That's the number to use. What's the acceleration? -10 meters per second squared. How fast is it traveling after 9 seconds? Well, you can just count seconds. Just when you drop it, it starts at 0. After 1 second, it's going to be going -10. After 2 seconds, it's going -20. 3 seconds, 4, 5, 6, 7, 8, 9. It'll be going -30, -40, -50, -60, -70, -80, -90. So there's the answer. Now, if you wanted to, you could use that formula and you could solve for change in velocity, because the initial velocity, I'll call it V0, is 0 meters per second. If we could get the change in velocity, we'd know the final velocity. So this we can rewrite as delta V over AT. So if I want change in velocity, it's just AT. Delta V equals A delta T. And the acceleration is -10. And the time is 9 seconds. So 9 times -10 is -90. So if it starts out at 0 and it changes by -90, you're going to end up at -90. Number 20, this is a straight up acceleration formula. Car traveling with a velocity of 14 meters per second speeds up to 20 meters per second. And it takes 2 seconds to do this. So I want to use change in velocity over change in time. And the change in velocity, the velocity goes from 14 to 20. So that's a change of +6. It adds 6. You could do the final 20 minus the initial 14 and you get 6. 6 meters per second. The time is 2 seconds. 6 over 2 is 3, and the units would be meters per second, meters per second squared.